Okay, good morning, everyone. Good afternoon to those of you on the East Coast. My name is Barry Reeker. I am a vertical market manager for food and beverage here at Evoqua. I am joined by Jose Molina, a process engineer and business developer. Together, we have 30 years of food and beverage organic wastewater experience. Without giving away Jose's age, I will suggest that the majority of those years are his. Today, we're going to be talking obviously about organic wastewater for food and bev processors. Presumably, you're either working in the business yourself or are a processor with a wastewater need or a sustainability goal. We're going to do a quick market overview, jump right into case studies, then go through some wastewater basics, how that influences technology selection, and finally finish with best practices and lessons learned. This is not going to be an extremely detailed, highly technical presentation. We're going to try to keep it high level. This is part of our wastewater excellence series. We did DAF last time. We're doing organic wastewater right now. Next time, we're going to do a deep dive into anaerobic pretreatment and then finally go into waste or water reuse and sustainability. Okay, why are we here? We're very lucky. We work in an awesome business, the food and beverage business, the water treatment business. Satisfying, clean, and enjoyable. We facilitate what life is all about, which is the picture that you see on the right-hand side. It's a great business, but it is a business. So when we're talking organic wastewater, we're talking about typically a large capital purchase that could, last for 20 or 30 years. We're talking about permit limits getting tighter and costs rising. We're talking about water and wastewater being as much as 30% of your total overall operating costs. So when we're talking organic wastewater treatment, there are competitive implications here. Of course, if you don't have a wastewater treatment plant or your plant is out of compliance, you're not producing anything. And water is an environmental issue and a social issue. Of course, we all care about it, and it's also important to our brand, which consumers respond to as well. This is a fun image, I thought. This image is from, this was a map from 1922. The greatness of the US is founded on agriculture. I would argue that it still is, and even though the imagery may have changed in 2021, food and beverage is ubiquitous, and we have processing coast to coast in the country. So speaking of, we've got, at last count, about 12,000 food and bev processors in North America. Everybody's got the similar water and wastewater needs. We need clean water to put in our products or to contact our products, and then we need to clean that water when we're done with it to either use it again or discharge it to the city or the river. What's interesting and what we'll spend some time on here today is that even though the needs are the same, the local variables have a huge impact on what technology selection is right for your plant. We've got a varying degree of water expertise in-house, depending on whether you're a privately owned, smaller regional processor or part of a multinational business. And we've got different ideas on how to go about executing wastewater treatment systems. The one thing everybody has in common, nobody wants to get wastewater wrong. So we'll help you try to make sure that doesn't happen today. Looking at market trends, all I want to highlight here is down at the bottom, food and bevs, 6.5% growth year over year, even in or despite of COVID. And then on the right-hand side, we have capital spending. We have project count at the bottom, and we have project dollar value at the top. The green lines are new facilities. The orange lines are in-plant capital projects. What are we spending capital on? On the BEV side, as you'd imagine, with water as an ingredient, most of the equipment is process water oriented. When you look at food, it flips. We still have lots of processed water needs, but the wastewater is higher strength and the costs are higher, so it flips. The distilling and brewery industry actually match the food industry more than they do the rest of the beverage category. Fermentation, distillation processes producing high strength wastewaters, both soluble and insoluble BOD. And again, you see more capital spending on the back of the plant. What technologies are growing? Here we're looking at a comparison between 2019 and 24, a projection, I should say. What's expected to win? What are people thinking about? Sustainability, reuse, and digitalization. Sustainability here for anaerobic treatment, super low operating cost, no energy input, efficient removal of BOD, and biogas, renewable energy as a byproduct. Makes a lot of sense. Reuse, microfiltration, ultrafiltration, membrane separation, purifying water to either use it in the plant again or to discharge it to a river. And then on digitalization, we see controls and monitoring down here at 4.3%. Okay, quick sales pitch on Evoqua, if you will. Evoqua touches water, all aspects of the water cycle, so from municipality to industry to commercial and back again. Speaking specifically about the industrial market, we have over 1,000 organic wastewater installations. Over 400 of those are biological systems, consisting of our 5 anaerobic processes and our 4 aerobic processes. Of course, hundreds of phys-chem installations, both as pre-treatment, primary treatment, or for polishing. We do have the largest service network in North America. We operate everything we sell, and we execute these projects as equipment, design, build, or build, own, operate. Thank you. This is a quick peek at the reference installation map. As you can see, there's typically an Evoqua installation somewhere near you, should you like to go visit one. And with that said, I will hand it over to Jose to do case studies.
Thank you, Barry. Can you hear me okay? Hey, Barry. So the question I'd like to ask you all, if you're involved in the food and beverage market, is what's in your wastewater? Kind of like that, what's in your wallet question. What is in your wastewater? So when you're talking about the food and beverage industry, each plant will be unique, of course, but there are some common elements to all food and beverage processing wastewater food and beverage processing plants. So when you look at your wastewater will look a lot like your final product. So if you're making soup and putting that soup in a can, your wastewater will look similar to what that soup is, plus a lot of wastewater. So wasted product, lost product, and then cleanings from your CIP lines and things like that. If you can look at it in a different way, your wastewater will look a lot like the kitchen sink drain would look like if you were to make this product in your kitchen sink or in your garage if you're brewing, if you're making beer. So I thought I would come up with 4 examples that I wanted to discuss, look at the common elements and also at the differences. So I've picked some of my favorite things. So beer, French fries, candy bar, and yogurt. If I can get into the first one, Barry, please. So the first example we wanted to look at was a brewery. So this is a relatively new plant built in the last 3 or 4 years. This was a greenfield site on the East Coast, what you would call a showcase plant for this company. So you have concerns about neighbors, you have concerns about being an environmental leader in your field, commitment to sustainability, but also you have to look at your local needs. You are trying to meet your sewer guidelines. You're hoping to simplify your solids handling. So in this case, the brewery wanted to be able to treat the wastewater and not have to worry about separating the spent yeast, separating the spent hops, and having to find an outlet for those materials. So our solution was an anaerobic membrane bioreactor. It's a system that is able to treat the wastewater as it comes without any pre-treatment. It's a relatively high organic strength COD of 10,000 milligrams per liter or more, and very high TSS as well. So very elegant solution in a compact site, converting 98% plus of the COD into valuable biogas. Another example we thought we should touch on is a large potato processing facility. So they're making French fries at this plant. Of course, your wastewater will be what comes out of managing, handling the potatoes that come into the plant, right? So there'll be peels, small pieces of potato. As you cut the potato into the shape of a French fry, you will have product loss. You have little bits of material that end up in your wastewater. In this case, the particulates and the FOG would represent over 20% of your total COD load. One choice you have here is to separate those solids and that FOG and handle it some other way, and then only treat the soluble portion of the COD. The choice that we followed in our case here was to leave the TSS and the FOG in the wastewater and digest it all in a single unit that can do over 85% COD removal in one single step. Of course, the anaerobic reactor converts most of that COD into biogas, which you can utilize, but there is still some organic matter left over. There's also nitrogen and phosphorus left over in the wastewater. For this plant to be able to direct discharge their treated effluent, we had to go back and do a second phase where an aerobic MBR system was put in to be able to do phosphorus and nitrogen removal to meet direct discharge quality objectives.
What does that mean, Jose? That wouldn't have been practical without pretreatment.
Yes, thank you. Yeah, so the point here is that the treating the full load aerobically only to be able to do biological nutrient removal, it would have meant treating a very large organic load. So the operating cost of treating a large COD load aerobically only, for when we're talking about over 1 million gallons per day of wastewater, it would have been a very, very high operating cost endeavor. A lot of sludge would have been generated by this system. In this case, so we've optimized the unit operation so that the organic load, the COD and BOD and the TSS get treated anaerobically, and then we use the aerobic system just for the remaining BOD, plus then you're able to do the removal of nitrogen and phosphorus prior to direct discharge. Another interesting example, there's a candy manufacturing plant in the US. The original system consisted of a DAF unit to remove suspended solids and FOG, and that was followed by an aerobic treatment system. So elegant solution, it took care of what it needed to do, which was to remove both TSS and FOG as well as some of the BOD in the wastewater. However, as production increased at this plant, the operating costs were getting to be out of hand. So the more wastewater you have, the more wastewater you treat in a DAF unit for separating the solids and the fat, oil, and grease, the more you're handling sludge, the more you're adding chemicals. So it's a very high operating cost issue. The aerobic treatment system that was following, you still have 60 to 70% of the organic load still needed to be treated aerobically. There as well, you're spending money on electricity, you're spending a lot of money on sludge disposal. Our solution here was kind of an interesting one. So we were able to treat the raw wastewater at this plant anaerobically with that anaerobic digester that you see on the right in the photo. That reactor itself is able to receive the suspended solids and the FOG that's present in the wastewater. So we were able to remove the DAF unit. So we were able to eliminate the high operating costs associated with the DAF, and instead we were treating most of the organic load anaerobically in the digester, converting that COD load into biogas and being able to utilize it in a process boiler. When you do that, then now you're removing 90% of the organic load. The downstream aerobic system, which you see on the left, was able to continue to operate, but now treating only a fraction of the load that it used to have to treat in the past. The aerobic sludge here is sent to the anaerobic digester for even further digestion and even more biogas. So we thought that was a very elegant solution to wastewater that contained quite a bit of suspended solids and fat, oil, and grease that needed to be treated. So finally, we have another example of a dairy plant. This is a yogurt processing plant out on the West Coast. And normally this would have been a very good candidate for anaerobic treatment. However, when you start looking at the local forces, local variables that we need to take into account, where you needed to reduce quite a bit of nitrogen and phosphorus for direct discharge, anaerobic treatment was no longer the slam dunk that we would have thought it was, because you have, again, the other objectives to meet at the same time. So the solution we came up with was instead to go directly into an aerobic treatment system. So an aerobic MBR is a relatively compact technology. It gives you a very high quality effluent. And at the same time, it allows you to remove nitrogen and phosphorus to meet your objectives. Okay, next. So those were 4 examples where we were able to come up with 4 quite different solutions. So let's put that into context here. So these are just schematics. Don't get into too much into the details. But let's look at what each technology can do and cannot do. So as we were saying earlier, a primary treatment unit such as a DAF, which is something that was covered in a previous webinar, a DAF will address the particulate or the floatable portion of the organic load in the wastewater. So if you have a very, very dense, whether it's a food processing wastewater that has a lot of oil and grease or solids, and especially those solids, you could find an outlet for them so that you could maybe sell them as livestock feed, then it makes sense to look at a DAF either on its own or as part of an overall treatment system using other technologies downstream. But let's just look at what the DAF will do for you. It will remove anything that can be floated out. So if it's solids, organic solids, or fat, oil, and grease, we will float them out, and the associated COD that comes with it will be removed. So some wastewater, you'll be removing only maybe 10% of your COD, and there might be some wastewaters where you're removing 50% of your COD by floating it out. This solution is relatively low in capital cost, but it will have relatively high operating costs. You're having to add chemicals to coagulate and float out the solids, and you are paying for somebody to take that sludge away from your plant. If you can find somebody to buy it off of you, or if you can find somebody who can transport it out of your site for free, then that would be an advantage. Of course, if your downstream process is an aerobic only process, you have reduced the amount of load that needs to be treated in the downstream system. Going over to the next treatment process, generally speaking, aerobic treatment will get you the cleanest possible effluent. So out of 100 kilograms of COD that come with the wastewater, you might discharge 2 to 10 kilograms of COD. So 90 to 98% of the COD can be removed aerobically. There is a price to pay, of course. So you're paying for aeration. So quite a bit of electricity needs to be spent to treat that wastewater aerobically. You are converting most of that organic load into COD, so that's heat loss, but you're also growing quite a bit of biomass. So that biomass, that waste sludge needs to be handled and taken off site. So again, it gives you quite clean effluent, but it's a high operating cost solution to treating your wastewater. So when you have the right conditions, then what you might want to do is combine the aerobic system as a final step and have pretreatment either as a DAF with the solids that you separate, that you saw on the left, or maybe ideally what you want to do is treat that wastewater anaerobically. So anaerobic treatment is the most energy efficient, the most sustainable way of treating a waste product. It will convert most of the COD or organic load into a biogas. So rather than us having to input energy in the way of aeration, electrical energy into aeration, what we're doing is we're drawing off a biogas, which can be a source of green energy for the plant. You're also generating very little bit in terms of waste sludge. So out of 100 kilograms of COD that comes in, you might generate 5 kilograms of waste biomass that you need to dispose of. One small drawback, if you compare it to aerobic treatment, is the fact that the quality of that effluent that comes out of an anaerobic treatment system, generally speaking, will not be as clean as what comes out of an aerobic treatment system. What we often do then is combine that anaerobic treatment unit to the aerobic treatment unit downstream so that we can polish it off. Let's not get too into the details of this chart, but I think we need to make the point of how do you select? There's no perfect solution. There's no one single solution for any given plant. But generally speaking, we see on the vertical axis, as your wastewater gets stronger in terms of organic strength, in terms of COD, the more it will tend towards the technologies that you see towards the top of this chart. So whether it's an anaerobic membrane bioreactor or a regular anaerobic bioreactor, the stronger the COD, the more it favors those solutions. But then as you go from left to right, as you are looking for cleaner and cleaner effluent, anaerobic treatment alone will not get you to where you need to be, and you might need to follow the system with a aerobic, or even going beyond that, you get into UF membranes or RO if you have a very tight objective to meet at the back end. Where does the DAF sit in that? Anytime you have particulate or oil and grease in your wastewater, the stronger the better, again, because you get advantages in terms of flows, but you have to be mindful of the fact that the quality of the wastewater that comes out of a DAF may not meet all of your treatment objectives, but it's a good step. It can be a part of your solution. Okay, so the 4 examples that we showed earlier, the brewery, French fries, candy bar, and yogurt, even though the end product is quite different for each of those cases, the wastewaters that come out of those plants in a lot of ways are quite similar in terms of strength. For example, most of these examples that we're looking at, the COD of the raw wastewater in those plants can be on the order of 6,000 to 10,000 milligrams per liter. That's quite typical for most food and beverage processing plants. BOD will be a little bit more than half of the COD. And depending on what you're making in your plant, you can be looking at very relatively high TSS, high FOG, high nitrogen and phosphorus. Again, that has to do with the ingredients, that has to do with the products that are coming into your plant for you to make your food or beverage product. And how you tackle that wastewater, like we were saying earlier, will depend on the characteristics of the wastewater, on your objectives for final effluent, and on your local variables that will push you one way or the other. If you are can you go back please just for a second, Barry? So if you're in a site in a city that only is looking for you to remove the suspended solids and the FOG because those two might give the city problems in the sewer line, then a DAF is a nice, elegant solution, and then you're able to continue doing your production, which is what you want to concentrate on. But as your objectives change, so will your solution, and you will be looking at either an anaerobic or an aerobic or a combination of those two prior to discharging your wastewater. Thanks, Barry. So I was touching on this point. You always, as you get to know your wastewater, you also have to look at your local variables. What are your objectives? And that will help guide you towards the right solution for your plant. What are the city sewer permit conditions? Is the permit expected to change in the near future? is maybe the permit is not changing itself, but the fees that you pay for them will continue to increase. That will go into your technology selection or your solution selection. Do you expect your production plant to increase in size? As production goes up, a lot of treatment systems will proportionately go up in terms of operating costs. But the bigger the flow, the bigger the load, the more you will tend to look at anaerobic treatment as a more sustainable, both economically and environmentally, solution to your wastewater needs. Of course, this technology selection also pays a lot of attention to how much space you have available for doing the treatment. If you saw the photos that I was showing, a potato processing plant had plenty of space, so we were able to put in a relatively large reactor, which allowed the plant to treat the particulate part of the wastewater. And always you have to look at your sustainability goals. Are you looking to reduce your greenhouse or your carbon footprint? Are you looking in the future to reuse the water? Things like that will come into play as well. And finally, is your company okay with high capex, but looking for you to make up the difference in the long term by having low operating costs? So we're looking at the total cost of ownership of your treatment system. Like Barry was saying earlier, when you're talking wastewater, you want to think in the long term, because that plant will be there for 10, 20 years, 30 years, or perhaps beyond. So you want to get it right. And of course, you also want to make sure that the plant is something that's relatively simple to operate, because you don't want a whole crew of people having to operate a treatment plant. You want that plant to be as simple as possible. Okay, Barry, you were doing some summary here.
Yeah, sorry, I was on mute. Thank you, Jose, and repeating, reinforcing what you've said. There is a bit of an order of operations to it. It's not hard and fast, but if you had your choice, you would put in the anaerobic system first, and then you could right size your aerobic system or your polishing system of some sort. You're not designing that polishing system for the full raw wastewater load. You're designing it to treat 10% of the raw load, because your pretreatment system is removing 90% of it. So if you need, let's say, 50% of your flow for reuse, then you only need to size that system for 50% of the flow. The other way around, even if you already have an aerobic treatment system, which many plants do, they maybe start with a DAF, evolve into an aerobic system, and then they've outgrown that. You still need to put the anaerobic treatment system first in terms of the process train. You will never see an anaerobic system following an aerobic system for the reasons we've mentioned. The DAF, of course, is flexible. It can stand alone. It can be used just for solid separation. It can be used as part of an aerobic system for biosolid separation. Okay, again, a lot of repeat here, so I'm not going to spend a lot of time on these slides. DAF has the lowest capital costs, probably has the highest operating costs. It's targeting the soluble COD. You're going to use it when you've got a high ratio of TSS to COD. You can use it when you've got a friendly permit and your surcharge isn't that bad. You can use it for pee removal, and you can use it if you can sell what the DAF separates off. If you can sell, animal fat back to a rendering plant, then that may be the thing that makes the most sense. The aerobic side, as Jose mentioned, best effluent quality, highest operating cost. Or sorry, this is the anaerobic one. Sorry, most efficient removal, lowest operating cost, renewable energy as a byproduct. We use it for high strength wastewater. We use it when we care about sustainability, and we use it when we're thinking long term about the total cost. The aerobic side being the best effluent quality, the highest operating costs. We're using it when we've got a strict limit to hit. So whether it's a discharge limit or it's an internally imposed limit for reuse, we use aerobic treatment. We use aerobic treatment for nutrient removal. And we use aerobic treatment when there just isn't enough flow or load to warrant any pre-treatment system. So, sometimes, like the dairy example that you saw there, even though the wastewater was strong, it was less than 100,000 gallons a day. The aerobic system was fabricated somewhere off-site and shipped there on a truck, so it was quick, efficient, and high quality. Made sense for them. Beginning the wrap up. We haven't talked much about what goes on in the plant, but obviously the less stuff that goes down the drain, the smaller your wastewater treatment is going to be. So to the extent that you can eliminate that and do operator training and realize production efficiencies, that's going to have a direct impact on the size of and technology selection you choose for your wastewater treatment plant. I would also stress that understanding the total cost of ownership is key. You might not want to sign up for something for 20 years that appears to be low cost today, but puts a burden on your business in terms of, it's easy to underestimate hauling costs and energy costs and things like that. But those are things that tend to climb and increase over the years and become a burden. What else would I say? Know your wastewater. Big investments, serious consequences, as we've talked about. Spend the time on characterization. Get the composite sampler in there. Understand what your wastewater looks like on a daily basis, both daily and seasonal variations. And that is small money that pays huge dividends over time. You want to make sure that whatever you design is representative of your flows, and then also that you've put some thought into what your flows are going to look like in the long term if you're considering your production expansion. Or maybe there's a dietary trend or change out there, and you're going to start producing something else. Well, what's that going to make my wastewater look like in 6 months or 2 or 3 years? As Jose was talking about, sometimes there's a decision between, we're talking about food waste here, high strength or organic stuff. So it has energy value if you put it in an anaerobic digester, but it's also got value as a residual, maybe for animal feed or maybe to a rendering plant example, like we were saying. So you kind of get to do that cost benefit analysis to see what's the best, platform for you to build from. Sustainability, of course, like Jose said, yes, we're thinking about future needs now. So if I'm going to have a reuse need or I'm in an area with low availability of water, that's going to play a role in my wastewater treatment evolution plan. We've addressed the rest of these points here. So in summary, as you guys have heard, this is a game of trade-offs. There are pros and cons to different ways of going about it. And it's not that there's not one right answer, it's that there can be more than one right answer for each plant and each problem. And the more time you spend thinking about what you have and who you want to be, the more clear the path that you should go down will be. Yes, as I mentioned, investing in your production efficiencies. The best wastewater treatment plant is no wastewater treatment plant. If you can have all of your, material go to product. Invest in characterization, as you just mentioned. Think long term, and if possible, seek input from a consultant. I know there's several on the phone here right now, or a vendor that has the ability to help you understand the implications of different choices. Sometimes you send a basis of design out there and everybody gets the same basis of design, but they can all interpret it differently depending on what capabilities they have in-house. So that's certainly a good way to protect yourself from making a wastewater mistake. So with that said, we will wrap it up and open it up to questions if there are any. Thank you. Probably should have set this up earlier, guys, but there is a question box there. Okay. Thank you. Can I speak to the difference between SAF and DAF? No, I can't. Whitney, the last session we did was a dissolved air flotation orientated one, and we don't have our DAF expert on the line right now, but we'll follow up with you after with Patrick Pierce. Anyone else going once?
Yeah, I wonder, Barry, if an SAF would be just a different way of injecting the air into an air flotation unit. So whereas where a DAF is dissolved air flotation, there are units such as induced air flotation units, and maybe SAF would be just another variation on the same concept. But the idea is the same. You're putting in very small micro bubbles into your unit, and it's those micro bubbles that attach to the flocculated and coagulated solids and flow them to the top, and then you can remove them. So I would say there will be a variation on the same concept. The need to add chemistry really depends on the type of solids or oil and grease that you have, whether they're easily floatable or if there's a way to check if the solids are large enough already as it is to be able to float them up to the surface. The concept is the same. You're trying to separate by floating anything that will be in the particulate form.
Okay, we'll get some more questions rolling in here, which is good. Do you see biological pretreatment to sewer becoming more common for poultry processing? Well, yeah, if they have access to a sewer. Sometimes the problem with the big poultry processors is that they may not have access and they may prefer to land apply. But poultry processing industry has been using some form of biological treatment ever since biological treatment has been around. They do a lot of anaerobic systems as well. Hope that answers your question, Jonathan. Jose, question for you. Soluble COD means soluble in water with no additional chemistry, correct?
That is correct. So soluble COD is if you can think of things like milk. Milk will have soluble sugars in it. It will have soluble protein in it. But before milk left the barn, there would have been things that you could separate out. So the cream in milk, the organic load coming from the cream, that can float to the top. There might be coagulated solids, especially if you're making cheese. The cheese part, the parts of the milk that turn into cheese is actually proteins that come out of solution and become insoluble. So likewise in wastewater in general, anything that's soluble, that's in solution in the wastewater becomes soluble COD, and anything that you can separate out by gravity or by flotation, that would be your non-soluble COD particulates.
Okay, a few more good ones coming in here. I'm adding flock and microbubbles to my tank and it's floating to the top. What's the best way to remove them? Sounds like you're trying. Sounds like you should be skimming those off, Michael, but that's an application specific thing. We'll follow up with you directly afterwards. Next question. What is the best wastewater treatment system for slaughterhouses? Well, what we're trying to say here is that there isn't one, and I can't prescribe you the home run process because you got to look at the local variables. You know, what is the load? What is the discharge permit say? What is the nutrient limits? What are the sustainability goals? How efficiently is that facility using water? What is their access to fresh water? And what we're trying to suggest here is that while we've got all these puzzle pieces to use, you really need to go and understand the local plant variables in order to put the picture together. Is it possible to get a copy of the presentation? Of course, we'll send it out. Following aerobic, do you see more gravity like clarifiers or DAFs across the food and bev industry? Another great question. I think you used to see more clarifiers. I think you see a variety of both now. You could also have a membrane skid there now instead of a DAF. So when you think about it, it's the same thing as the slaughterhouse example. What quality water are you trying to get to? You can do conventional activated sludge into a gravity clarifier and produce quality effluent A. You could do the same thing followed by a DAF, separate more solids, produce a better effluent quality. Do the same thing again and put a membrane skid on the back, separate all solids with your membranes and produce the best effluent quality. So again, local variables.
Yeah, a big part of this pollution matrix has to do as well with, well, not only the objectives, what quality of water you need to meet, but also how much space do you have. So a DAF in a large settling pond will essentially do the same thing, but a large settling pond will take up more room. A DAF allows you to be more compact, have much more controlled conditions, and you get out that floated material that you get out is a lot thicker, so you have smaller volumes of waste sludge to remove. Getting back to the original question, yes, the conventional way of clarifying after aerobic would be a gravity clarifier. But as you said, Barry, membrane bioreactors, using physical membranes to stop the solids from getting out on your final effluent, they're becoming more and more common. Prices have come down, and there are lots of advantages to having something like a membrane bioreactor as part of your treatment system.
All right, sorry for the background noise. My son is here visiting. A couple more, and then we'll wrap up. Would mixing an EQ tank or a selector tank be considered anaerobic? No aeration needed. What in that where can I inject RAS? Yeah, okay. An EQ tank with no air, it can turn anaerobic, but it's not really truly an engineered anaerobic system. Yeah. I would not be attempting to recycle RAS back into that. We can talk to you.
Right. So I think you need to go into what the definition of anaerobic is. So if you're talking about anaerobic in the sense of methanogenic, true anaerobic digester, an EQ tank would not have enough retention time normally to be able to do that and do large COD removals anaerobically. But what you will see in an EQ tank that's not mixed and it has too much of a retention time, you will see septic conditions, you will see reducing conditions, and you could end up with odor problems because you start getting, the first thing that goes is the sulfate gets reduced down to sulfite, and you might get into odor problems. So other than not quite to the point of generating biogas, what you're doing is generating odors from the wastewater becoming septic. There is such a thing as anaerobic conditions in a short retention time tank when you're trying to do biological phosphorus removal, but that's a subject for a much later discussion, and I don't think that is what was the intent of the question here. Here it's, I guess, raw wastewater going into an EQ tank. It could be considered a selector tank if you were to recycle mixed liquor from downstream back to it as part of a process to remove phosphorus or as part of a process to get better settling sludge, but it would not be anaerobic in the sense of generating biogas, generating methane.
Okay. Thanks, Jose. Last one here to wrap up and segue. Is the anaerobic MBR process a new technology or well established? Do you have some reference installations? So it is relatively new. If there is such a thing, it is the sexy wastewater treatment technology of the time. We did our first anaerobic MBR in 2009. It is still out there running happily. We've since done 2 or 3 more anaerobic MBRs for the same client. We now have a total of 11 anaerobic MBRs out there on a variety of high strength food processing wastes and even on some biodiesel applications. So yes, we have lots of reference installations. Yes, we know the technology well. And I would encourage you to come to our next section or our next webinar where we're going to do the deep dive into anaerobic. We'll compare and contrast anaerobic MBR with the low rate, with the high rate, and see how all that works out. So thank you everybody for attending. Thank you for your questions and discussion. We enjoy doing this. We will distribute the presentation afterwards. Our contact information is there. And of course, we'd love to hear from you if you have any more questions. Thank you very much.